Hello, it's Keith here, and this is lesson 1 of my multi-platform tutorials. Now, last week we had a look at lesson 1 of the platform-specific tutorials, and in that lesson we wrote some code that allowed us to print characters to the screen and to read keys from the keyboard, and we wrote that code on all of the systems we're working on. That is the Amstrad CPC, the Enterprise, the MSX, the ZX Spectrum, and the TI-83 calculator. Now this week on the multi-platform series we're going to use that code and we're going to write a piece of Z80 code that will work on any of the systems that we have that multi-platform code for. So essentially we're going to write a piece of code that you could actually port to any system, provided you can code similar multi-platform code that will allow for key reading and text writing. Okay, what are we going to do today? Well, we're going to try and solve a problem that's likely to come up for us, and that is because we're working with multiple systems, we're going to be dealing with multiple emulators or multiple real systems. And in the past we've had the luxury of the Amstrad CPC, and the Amstrad CPC's debugger on WinApe has provided us with some very good functionality, and that it provided us with breakpoints that we can put into the source code. It's provided us with a monitor that allows us to see the registers of the system at any point, and it's given us debugging symbols, which means that if we pause the emulator you can see that the assembler has actually copied across the labels from the assembler to the debugger, and this makes working out what the code actually does far easier. But unfortunately on other systems we're not going to have that available to us, and in fact especially if we're dealing with real hardware and a bug on real hardware, we may have no debugging tools available to us. So what we're going to do today is we're going to write some simple little debugging tools that we can use to see the current state of the Z80, and we will be able to use these tools if we're in a situation where our code is malfunctioning and we need to work out why it's going wrong, or we just don't know what the system's doing and we need to see what the system, if the system's getting to specific points in the code, and what the status of certain registers are when it gets to those points. So we're going to write some simple monitoring and debugging tools today, and we're going to do all of that in Z80 assembly that will work on any system that we have the GetKey function we wrote last week, and also the PrintChar routine that we wrote last week. So this will work on all of the systems we're working on: the Amstrad CPC, the MSX, the Enterprise, the ZX Spectrum, and the TI-83 calculator, as you can see from these samples on the screen now. So let's have a look at the code then, and we'll see what we're going to be working with this week. So this week we're going to be using the Hello World example as a kind of template, and we're going to be adding some new functions to that so that we can monitor the status of the Z80 at various points in that code. And the functions we're going to create today are the Breakpoint function, which will stop the program's execution and show the program counter. And I'll just show you the purpose of that now. If you have a look at the TI-83 here, for example, it's showing 9DAB. Now, when we're running a program on one of these systems, we may not actually know the memory address that the code even resides at, and if we don't have very good debugging tools, we may struggle to work that out. But when we use this breakpoint function, or this breakpoint once function, the code will pause, show the current program counter, and wait for a key press. And this allows us to go in, and if we have one, open our debugger, and now all we need to do is find that location in memory. And if we look, this is our breakpoint here, and if we look at the code here below, we can see that this is the code we're actually seeing here. Now if you had to scan through all of the code that the execution could currently be occurring at, you would probably really struggle to even work out what piece of code you were looking at. So just a simple tool like this that shows us, well, at this point in your code where you've put this breakpoint is where the Z80 got to, and that's the address that it is residing in memory. This can allow us to debug our code quite effectively. And of course this only pauses for a moment while we debug it, and then if we just close this and press a key, you'll see our execution carries on normally. So this is a great way of stopping execution, so that you can firstly check that execution actually got to that stage before a crash occurred, but then see what the breakpoint is, check the code, do any other changes you want, maybe add more breakpoints with the debugger itself if you have one, but then once you're satisfied that you've done everything you need to, carry on the program as if nothing had happened. And all of the code we're going to look at today, all the debugging tools, make no changes to the registers of the Z80, so they should make no difference to the normal execution of your program. So you should be able to put them in for your debugging, but apart from a slight increase in file size, they won't actually change the running operation of the Z80, and that's going to be very important. So we've got breakpoint once, and this function is designed to work in a loop because it will only occur once. Once the breakpoint has occurred a single time, it will actually delete itself from the source code from the memory by self-modifying the memory. Breakpoint is just a simpler version which will break every time. So you see this loop will actually run 3 times, but the breakpoint only occurred once because of that self-modifying code in breakpoint once. Now, beyond that, we've got a monitor function, and this will actually show the status of all of the Z80's registers. And then finally, we've got a pushed register function, which is a very simple version of our monitoring. And all we do is we push a single register pair to the stack, run this function. This function will consume that, taking it off the stack, and show it to screen in exactly the same way as our breakpoint did. So just surrounded by stars there. So that 805D there is the HL we pushed here. So if we want to check the value of HL because we're concerned it's been changed, or we simply do not know what it is, we can just push it onto the stack, call this push register. The HL is taken away so that print string will not have any problem with that. So we can monitor HL status just with this command. And of course, instead of HL, we could use AF or IX or whatever we wanted. So that's the functions we're going to be doing today. So in addition, we can use a more limited monitor. All we do is we rem out monitor full here, and then if we recompile, now this version will use less memory and it will only show the basic registers of the system. So let's have a look at that. We'll just call and 8000 here. And you see the functionality is basically the same, but now we've only got the primary registers, not the shadow registers. We've lost the interrupt status, and also we've lost the showing of IX and IY. But that may well be enough for general purposes, and as I say, this version uses less memory in the compile, so may be more appropriate when memory is limited or our program's very big. So let's have a look at how these programs actually work today. So you can see at the bottom here are all the commands we're using. We've got the definition of monitor full, which is if we want to have all of those registers. We've got an option here to disable the pause if we don't want the pausing to occur for that key press on all of our functions today. The monitor script here is the main monitor function which shows all of the registers and the interrupt status. Then we've got this simple version which is just for our breakpoints and our push register, which is much smaller, so if we don't have much memory or we don't need the full functionality, that's going to be preferable to us. Now both of the functions today use this show hex command, and we're going to have a look at that first. And all that does is it shows a HL pair as hexadecimal on screen. So let's make a start and have a look at that show hex command. So here it is, and you may remember from, I believe it was lesson 8 of the basic series, I mentioned that the DAA command could actually be used to convert a byte into a single hexadecimal character. And so all we're doing here is we're taking the high nibble here, shifting it to the right so that it becomes the low nibble, calling this PrintChar function here. Now this is a bit of sort of magic if. So all we do here is to clear the carry flag, which is important for DAA to work correctly. Then we run this DAA, and all that does is it converts a 0 to 15 in that nibble to a 0 to F as a character that we can show on our screen. And then we call the PrintChar routine. And you notice we've done a slightly tricky optimization here. We use PrintHexChar here for the first nibble, and then PrintHexChar here for the second nibble. But rather than using 2 calls, we actually exploit the fact that this one will loop down here and then jump back to here and then flow back into that same function here. So that's a trick that occasionally may be useful to you to know. Okay, so that's this function will just take a single byte and show it to screen, and then we will proceed on by looking at this monitor simple function. And this is the more basic functions for just showing individual hexadecimal register pairs, or for showing the program counter. So let's have a look at that. So you can see here there are 3 functions this is providing: pushed register, breakpoint once, and then there is this sort of function that's used internally called Breakpoint Show. We'll have a look at Breakpoint Show because it's used by all the other functions. So all Breakpoint Show does is it backs up AF because we, as I said before, we're not changing any registers that the Z80 uses. So we back up AF, then we load a star because we're showing a star on the screen around the register pair. So we show a star to the screen, then we load in our first byte from H, the high byte, and we show that it's hexadecimal, because as I said before, this show hex will show both characters of a byte onto the screen. Then we load the low byte, show that as well, print another star, and then we pause if we've been asked to. We restore AF and then we return. So AF has not been changed. Nothing's been changed because we're relying on our PrintChar function retaining all of our register values. So everything will carry on exactly as it did. Now, the first case of this breakpoint show is our simple pushed register function. So let's have a look at that. So all we do is we back up HL because we don't want to use the stack for backing up registers. So we're using our self-modifying code here. And then we pop a value off the stack. And the value that this will get is actually the return address of the code that called the push register function. Our next command is to exchange the value on the stack with HL. Now, the value we will be getting off the stack into HL is this value that was pushed that we want to show. And because we're exchanging, we're now swapping the return address back onto the stack, and the stack is now at the state we want it to be when we return to the code, because the return address is there, and we now have HL as we now have the pushed value as HL that we want to show. So all we do is call our breakpoint show function down here, which will show HL to the screen, restore HL back to the state it was before so that our code runs normally, and return, which will carry on fine. So that's all we need to do. Very simple. Now on to our next function, which is the simple breakpoint command. Now remember, this will break every single time this command is called, and so this is very simple. All we do is we take the value off the stack, which is the next memory address that will be executed, show it to screen, and then put it back on the stack because we want to return to it to carry on our code. Very simple. That's all it does. Now breakpoint 1's a little bit more tricky. Again, we take the return address off the stack, show it to the screen, and now we need to just back up 2 registers here because we're going to need them. So what do? Well, firstly we clear A, we set it to 0, and that's because this will save a little bit of memory here. Rather than setting each of these to 0 here, it saves a little bit of memory just by using A. So what we do is we decrease HL, so this is the first byte before the return address. Now bear in mind the call to this address will be 3 bytes. So what we're doing is we're wiping the first, second and third byte that preceded the calling address. Now let's have a look at actually what that does. So if we just run this program again, call and 8000. Oh, we do need to reassemble. Sorry, my mistake there. Because as I said before, this only executes once. So if we just do call and 8000, 8016 here. So if we go to our debugger and pause, go to 8016. Now you'll see here we've got this call monitor breakpoint once, which is currently actually executing. So if we just put a breakpoint here and continue, now you'll see we're now at that pop HL, which was the next command that was about to run. But if we scroll up here, you can see the call to this show breakpoint function has now been changed to 3 no-ops, and that's how we make sure that it only executes once, by changing the preceding 3 bytes that made up the call address. And that's what this does here. Then we just restore HL and AF, swap the address we showed back onto the stack, and then return. And that's it. Okay, so that's our simple monitoring functions that will do the basics of just showing a single register or a single breakpoint. Now let's have a look at the far more complex monitor function. Now this shows every single register in the system, and there's a few little tricks in here as well. And even if you're not interested in coding this monitor, and I'm not seriously expecting you to actually type all this in, you can just download it from my website. But even if you're not interested in this monitor function, there's some quite clever tricks in here that I think you'll want to see. And the first one of them is right at the top here. Now this function is called monitor EI check, and what this does is it actually checks the interrupt state of the system, and by that I mean, are interrupts enabled or are they disabled? And the way you do this is rather unusual. We looked at in lesson 8 how to use the I register as a sort of temporary spare register, but when we load the I register into a secret thing happens. If interrupts were disabled, the PO flag is set, And this is, it's documented in the Z80 documentation, but it's not exactly apparent that should happen, but it does. And what we can do is we can take advantage of it in this case, because it allows us to check if interrupts were enabled and disabled. And that means we can disable interrupts in our code and then only re-enable them later if they were enabled before we disabled them. And that's what we do here. We have 2 bytes here we're setting, and we're going to use these for self-modifying code. Now, F3 here is our disable interrupts command, but if we return here, then that means that interrupts were disabled. If we get to this point, interrupts were enabled, and so we change that F3 to an FB so that when we modify our code, we are turning the interrupts back on. And then the second byte here, 44, is the letter D, and that's for our visual label. We just increment it by 1 because we now want it to show in E for EI, and then we can use the B byte for our label and the C byte for our self-modifying code, and that's exactly what we do next. So that was just a little function we wanted to cover first. Now let's get on to the proper one. Here is the monitor, and the very first thing we do is if we're using the full monitor, which is where we do look at interrupts, then what we do is we check the interrupt. We run this check interrupt status function. We then use our self-modifying code to re-enable interrupts if that's what we're doing. Then we load this monitor special, which is just a label at the bottom of the code that we show on screen later, with the D or the E as required. And now we flow into our main code, and here it is. Now at the start, what we do is we push every single register that we're interested in onto the stack. And the reason we do this is we need a way of reading all of the registers one by one, and also we're going to need some of them in our code, and so we're simultaneously storing them for the purpose of viewing and backing them up. And you'll notice there's a few little tricks in here for reading I and R, pushing them on the stack. And so here we've got every single register we're interested in onto the stack, and then we start our main code here. Now what this does here is it works out what the stack pointer address was before we started all of our pushing, just by subtraction, and it stores that onto the stack in HL as well. And then we back up the stack, and then we copy the stack pointer via self-modifying code into DE, because we're going to use DE as an address pointer to point to the bytes we want to show to screen. The other thing we do is we load HL with the text labels, which I'll just show you quickly down here. Here's the text labels we're going to show. So we load the text labels in HL, the address of the actual data in DE, and we load B with the number of labels we're going to show. So here's our main loop, and first we show the 2 characters of the label, and then what we do is we increase DE because we need to remember our system is a little endian system, which means the bytes are actually reversed in memory to the way that the user will expect to see them. So we have to increase DE, read in the byte, show it to screen, decrease DE, read in the byte, then move along 2 bytes so that we get the next one, and then show that second byte to screen. And this will show the bytes in the way the user will normally expect to see. Finally, we increase HL, which moves us to the next label, and then we loop again to show the next register pair. And that will do all of the normal normal registers, including the stack pointer and the program counter. So that will get us all the way down to here. Now the last thing we do is just a simple little loop here, and all that does is it shows the 2 so-called special characters, which at the current state of the code is just whether interrupts were enabled or disabled. Now of course you could extend this function even further if you had requirements to see the status of the ROM mapping or the RAM bank mapping. You could add the code to do that, and you could maybe add a few extra characters here to this monitor special to show the bank number or whatever else you were interested in seeing. I mean, really, this is something that you could extend further if you required. Of course, you are limited by memory, because the more complex this code is, the more of the system memory it's using. But I thought this was a nice starting point to allow you to do some simple debugging, and also it does show some interesting tricks with regards to modifying the stack pointer using pushing to read registers that you can't easily normally read, and so forth. So by the time we get to this point, everything's done. We just need to remove that stack pointer that we pushed on from the stack, and then we do our pause, and we do the pause at this point so that we haven't changed restored any of the registers yet, and then we just start restoring all of our registers down here. At this point we get to this no-op, but by the time we actually get to this no-op will be modified by self-modifying code, and it will either be a disable or enable interrupts here, and then we return back to the system. And that's it. So a nice little function here. Some clever tricks maybe. It took a little bit of while for me to code and debug, but it is quite useful. So what do we want? What might we want to use this for? Well, let me show you what I've been using it for. So let's just copy this code here, and we'll put it right at the start of the function so that we can see it first. So all we're going to do, if I open up, now we're going to have a look at one of the modules we looked at last week on the ZX Spectrum. So here we are, ZX function here, and if you remember, this RST2 command was actually showing a character to the screen. So character 22 is a bit tricky, so we're not going to show that. What we're going to show is a plain letter A, and we just need to modify this up here. So we're not building for CPC, we're building for ZX Spectrum. And let's compile that here. So what we're going to do is we're going to show the status of the registers, we're going to print an A to the screen, and then we're going to show the status of the registers. And I'll just bring in my main window here. So my development tools now are available for download from my website, so please have a look if you're interested in acquiring these. They are quite tricky to use, but unfortunately that's just the nature of the beast. This is a complex thing we're doing, and there's a lot of scripts here, but I think they will save you a lot of time. Now, one thing I do need to point out is the tie calculator function and the MSX disk function will not work without a ROM file being downloaded and installed. Unfortunately, because of licensing, I'm not able to provide the ROM with the download, so please bear with me on that. But you can get these and should just be able to add that ROM relatively easily. So anyway, so all we're going to do to start our ZX Spectrum is we're going to use one of these here, depending on whether we want to use a disk image, a tape image, or a TRD image. Let's use the TRD image. So here's the first register call here before the letter A was shown to screen. So I'm just going to press a key. You can see the A was shown here, and now here's the registers again. Now, what has that actually done? Well, you may remember before we were talking about backing up our registers to make sure that the function hadn't changed anything. And what this has done is it's shown the status before and after our function call of all the registers. So now we can just visually compare on screen, and we can see that actually none of the registers have been changed except for AF, and of course the program counter, which is just the current location in memory. But AF has changed, of course, because we've changed it to a letter A, but none of the others have actually changed. And that does actually suggest that maybe my code is being a bit excessive here, because I'm backing up all these registers here, and maybe there's no need for me to, because possibly none of them change. Now, the only difficulty there is, of course, there may be circumstances with more complex functions like this locate command where some of these other registers do change, but as I say, the initial signs are that I'm being overcautious here with all this push popping. Maybe I don't need to, but this is the kind of thing that where having these monitor functions do make things a lot easier for me, because I don't need to rely on trying to add breakpoints, because on this debugger I have to add breakpoints at the command line here by typing $, and the memory address, and I don't even know the memory address of that line in the code. So I'd have to start scanning through the code to even figure out where to put that breakpoint. And so having just a simple little function here, like call monitor, that allows me to see the status of all my registers and allows me to create this kind of test code just to check my code isn't corrupting registers, to check it's behaving in the way I'm expecting it to, makes things really easy for me. And so there we go. So that's just what I wanted to show you today. Now, I'm probably never going to show you this program again, because it's not really something we're going to extend any further than today, or at least I don't plan to. However, please bear in mind that I will be using it all through my development for testing and debugging of the code that I show you every week, because I personally think this is more than adequate for most debugging purposes, and because it's something I've written myself in Common Z80 code, I can use it in the same way on all the systems I'm developing for without having to worry about learning to use all of the different debuggers and monitors that the different emulators provide, if they even provide a viable monitor debugger. So please go to my website. I'll give you the link below. The multi-platform lessons have their own subpage, and if you want to get the development tools I'm using today, please click on this toolbox link here and you will be provided with a link to learn how to download and use them. There is a YouTube video as well showing the basics of these tools, so please watch that as well, because as I say, they are quite complex to get started, but I can assure you that if you use these tools, you will be able to develop for all of these systems in minutes, whereas if you downloaded all of the tools that I've compiled together and written pre-usable scripts for, you will spend days, potentially even weeks, getting them working to the standard that I've provided here, because that's how long it took me to get them working to this standard. So I'd recommend, if you want to start playing with multi-platform development, to get these tools and scripts, and then maybe just branch away from the way I'm using them and use them in whatever way you feel you want to. But on the website, as always, we're going through the code, discussing all of the technical features of how it works, and hopefully it will explain all of the details to you. Now, as always, the files are in the sources 7-zip. It's the same sources download every week for all of my tutorials. I just keep adding more and more files to them, so please go ahead and download that. And if you want to try this debugger, give it a go. Any comments, let me know. Can you think of any other ways we could improve this monitor debugger? Let me know that as well. Thanks for watching again. Goodbye now.